will talk about the fibration of algebras.
First of all, this research is in collaboration from ebook. So I started looking into this with some matters data from the point of view that I'm going to tell about now, but Fosco has been also looking into this with elegant data. So we are looking into the same thing. Yeah, sure. Let's try to combine our forces and see what we can do. So, what is the fibration of algebras? Well, first of all, by algebras we mean, well, in the biggest sense we mean algebras where some end of function. Given an end of function, we can construct the pedigree algebras, which is just tuples and object of the underlying pedigree, and a map including the structure of the algebra. But in practice, it is not at all uncommon for our end functors to come in some kind of way to depend on some parameter, and it's useful to take it into account this dependence and really see what additional information this gives us and what we can do with this additional data. So a simple example would be if our category has just the categorical Cartesian product, then any object will induce an interfunctor which will map some object x into the Cartesian product of this fixed object and x. So this is a very this is basically always available, and this dependence can be encoded like if our end functors depend on some parameter, and this parameter is an object of some category, then well, it would like this to be a functorial dependence. So we will consider families of end functors which are given by a functor from some category into the category of end functors on this category on which are end functors. Now, it is quite, I think, conceptually helpful to think about this functor instead in the adjoint form, where we take some object of the category of parameters on of the underlying category, and consider this dependence as an action of the category parameters on the underlying category. So, in essence, we have a category which is acting on a category in a very weak sense. But, I mean, there are lots of examples of this situation precisely because of the weakness of this definition. So, if you have this dependence, then we can form the category which groups all of the categories of algebras or all of the parameters together. We can essentially take the fibration of all the algebras which can be constructed if one desires as the coordinate construction of the function which maps an object of A to the category of algebras over the interfunctor which corresponds to the parameter. Don't just look at the total category of all the algebras or all the parameters, which will be able to denote by this notation. So A is the category of parameters, X is the category, and we can consider the action which includes this dependence between A and X as just some implicit thing that exists as the two unit modules, and just use this very simple notation. So our objects are now triples: the parameter, the underlying object, and the algebra map. Well, this psi is just some morphism from AX to X, and since our functor is just an interfunctor, we don't require anything else. And well, we have this projection from this triple to A, which just forgets the underlying structure of the algebra and just gives the parameter A, and so the fibration over the category A and fiber over an object A, which is the category of algebras over the single interval. Now, of course, interfunctor algebras are nice, but we still sometimes, quite often, desire more structure on the functors and algebras. So, well, suppose that we instead have a functor from A into minus X. So this is also a similar dependence, except once we take the adjoint of the underlying functor, here we get a monad structure on each of these functors that are given our parameters. So we just now assume that these functors have some implicit structure of a monad included by this so-called action, which we will differentiate from the previous case by saying that A is acting on X via monads, while in the previous case A was acting on X via just interfunctors. And we can now again just do the same thing, except now our collective category of all the algebras or all the parameters has this extra condition that the objects of this triple are such that this psi is a monad algebra and more algebra over this monad structure that's this object that is monetary terms. Well, you can see that this similar thing would work with various like applications. Change this category of minus x for some category of say pointed functors 1x or functors x carrying some extra structure, and we'll be able to do a similar case. So we look at this construction from the point of view that we make two choices. So first we make a choice of how do our categories of parameters act on our underlying category. So either by monads or by endofunctors or by polyfunctors, whatever we need, and then we make the second choice of one concrete action, and then you can go through with this construct. Because both of these choices essentially comes the same thing, which will have different, of course, different properties, but we will assume that both of these choices are implicit, so we'll just need to use the same notation for all three cases, which is just fine, I think, because from the context, it will normally be able to know what is meant by this notation. And if it isn't, you can always make things a bit more explicit. Now, a simple example of action by monads is when we have a monadal category in which we view monoids. So, for example, a monad in set would be just a monad in the usual sense. In the category of Euler groups, we have rings, and well, each monad in C will induce a monad on the underlying category, which has as its algebras modules over this monad. And this is a natural situation, and the dual category of all the algebras, this fibration of algebras will be the category of left modules, and if we look at a single fiber, it's the category of left m modules over the single monad. Now, it is quite useful to not require that our monad lives in the same category as our objects. To, for example, we can have our monad be a monad in set, so a monad in the usual sense, and if our category C has two powers, well, each monad will induce a monad on C. So our monads can act on objects of C, and we can consider the category of objects of C carrying a monad action, which will be quite useful in some examples. Now, just to justify this point of view that this fibration of algebras is a centroid product, well, if you look at what is an object of this category, it is some object A, some object X, and an action of A and X. We can think about this algebra as an action of an object of the category A on the object X, and this functor from A to, let's say, monads X will encode what it means for objects of category A to act on objects of X. So, well, from this kind of data, we could, if like A and X were groups, for example, we could construct the symmetric product. So let's think about this piece of data as the formal symmetric product, like this actual object as, let's say, a single object of some, let's say, A or X may not correspond to this like in any direct way, but as a formal piece of data, this encodes the version just fine. Now, if you do look at the case of groups, then the symmetric product functor of groups, well, it has as its domain this category. This groups currently group action. So this is a short phrase to notice domain. Perhaps if you think about like the macroscopic principle, then it's not the one choice to make. But also our construction does depend on some action of A on X. So we are somehow taking this product of the category A with the category X. So again, this makes sense. And finally, well, if you look at this construction of this category A symmetric X, which depends on this action, then this itself as a functor, as a true functor, has as its domain the category which we can denote again as symmetric X, where the objects are triples consisting of one category, and in this case, this is constructed for the action of the Cartesian product of categories. So an algebra over such a action will be a functor from A times X to X. So precisely this kind of piece of data. So we're here considering the inner functor algebras. So again, by all the levels that we can consider, like the object lines level, the level of categories, and the two categories level, this makes sense as an notation. Now, since we are already considering this notation, it makes sense to further think about this as a symmetric product. So what can we do with symmetric products? We can consider diagrams like this. We have this symmetric product. We have two projections, which takes this triple here and just gets everything but the X component and gets everything but the A component. So this P is the fibration of algebras. Well, if we are, let's say, in the context of the product of groups, then this P should have a splitting. And it turns out that our functors, actually both P and V, will have kind of splitings, or at least adjoints on very big assumptions. So it is enough for X to have a terminal object for this P to have a right adjoint, which will be actually a splitting of P. So this is essentially, in most cases, a split edit. So like we should have it symmetric reproducing nice situations. Well, that's good. But B also has an adjoint as long as A has an initial object. Well, so we can now have this diagram of two adjoints, and you can see that now both X and A somehow map into this symmetric product. So this construction is looking more and more like a symmetric product. blah blah. And well, let's now consider what else would we want of this kind of diagram. If we were in groups, then this would add this map here, and this split AB here would hopefully form a split extension. But if we just have functors and categories, then this is a bit too much to wish for. However, if we restrict our attention to, let's say, some two category of, let's say, traposes, for example, or like some two category of categories which have some nice additive structure, then this is perhaps not too far from being true. So, for example, for traposes, we have this construction of an arcing code. If we have a left exact functor, then we can construct this new trapose, which will essentially be our fibration of algebras. Of course, has the dual version, which will be the fibration of co-algebras for categories that act via co-monads. So this is an example of this. If we define our action of the turbulence E on the turbulence E prime as follows, we just take this and simply action by co-monads, and the fibration of co-algebras will be the arcing. But this is of interest because this arcing moving will now actually be a nice extension. This will be an adjoint split extension, and actually every adjoint split extension will arise by this construction. So that's quite promising. So this was shown in this paper by for annual and superior. Now we will hope to have these kinds of results like also other two categories. So, so one property that we would be quite interested in is if we have some diagram of this form, then this will be of the same form as we had the two projections from the fibration of algebras. Well, when does this kind of diagram arise as the diagram of the fibration of algebras construction? Well, it has been proved that this is actually quite a simple answer. So this fibration of algebras is actually monadic over A times X. Well, that's quite nice, but it's actually monadic in the two category of fibrations over A. So it is monadic in a very special way. And as long as our diagram is such that the induced functor from E to X times A also satisfies this one. This is the condition which you can check, because this is just the narrow approximation X. There we can easily see that this when this is the case. So an example of monaticity for this construction would be this. So the category of congruent with both algebras over and correctly closed field of characteristic 0 has attached to it this kind of structure, this kind of diagram where we map from the algebra into real algebras via the primitive elements and into groups by taking the group-like elements, and this will turn out to be monadic. So actually we can essentially represent this category equivalent to Hopf algebras as the symmetric product of the category groups and the algebras. And this motivates lots of questions because so this is a very nice diagram for several reasons, and all of these categories are semi-abelian, so that's quite nice. And because, for example, ask if we deduce semi-abelian categories and take this construction, this fibration of also, the algebras and groups via their images into Hopf algebras from a torsion theory in this category. So, like in this category, we can always ask do these parts from a torsion theory, and when is a torsion theory like when does a torsion theory induce this kind of decomposition? So yeah, this is why I'm interested in this construction, because there are lots of promising fields of further research. So yeah, thank you.
Any question?
It may just be a comment, but this morning I spoke about comonadicity of elementary doctrines, and in fact we have a similar result for elementary vibrations, and I believe that the construction of the underlying factor for the comonad at that level is built in a form which is like yours, because we need groupoids instead of equivalence relations, and then actions of the groupoid, and it looks very much like that. We should talk about it, if you don't mind.
That's great. So yeah, this construction shows up in lots of places, but like it doesn't seem to have been considered seriously, really. So that's
Thank you very much.
So just to add that I'm going to speak about that construction.
Yes. So yes, we did it jointly, and you see what I mean. I can give you a preview of that.
Does this construction actually depend functorially on natural transformation between these parameterized functions? Do you get a function from these fibration?
So it depends in this kind of way. So these parameters A and X are not independent really. So if you want to look at this fibration of algebras construction as being parameterized by like A and X, then we need to consider how this parametricity interacts with these actions. So it is parameterized, yes, in a certain sense, and yes, for natural relations we can make it parametric, but it needs to care.
No other question. Let's let the speaker again.
Together, around 7:30, we can propose a restaurant da Pino. Pino, where